Thank you. All right. So hello, everyone. Welcome to the CS 201, the Computer Science Department seminar. So today it's my great pleasure to introduce Dr. Caiming Xiong from Salesforce Research. So Dr. Cai is the Managing Director of AI Research at Salesforce. He received his PhD in computer science from University at Buffalo in 2014. During his career, he has published more than 100 papers in deep learning, natural language processing, computer vision, and theoretical machine learning. He has won an Outstanding Paper Award at ACL 2019. He also served as area chair for a variety of conferences such as ACL and EMNLP, and co-organized many workshops at different AI conferences. So today, I believe he's going to talk about something on NLP happening at Salesforce Research. Yeah, please join me in welcoming Dr. Cai to give a Dr. Xiong to give a talk.
Okay, thanks, Chen. Thanks for the introduction, and also thanks for the invitation. Hello everyone. I'm Caiming Xiong. I'm a researcher from Salesforce Research. Today, I will talk about NLP mixed database. This is today's agenda. First, I will introduce some background, and then I'll talk about two components about NLP mixed databases. First one is about text-to-SQL. Another one that will be our main part for today's talk, text-to-SQL. Another part is some of our ongoing projects on natural accessible tables insights. And then I will conclude today's talk. The background. Databases are used everywhere. We use databases to store a lot of different informations, such as our financial information, like financial transactions, our healthcare information, like electronic health records, and some science, the documents and the experiment records, and our e-commerce intersection informations. So now, just in the web alone, it includes at least 2 billion static tables, and this number is growing. A lot of people in their work, they use data. They use data to talk with their customers. They use data to make a decision for their company or to make a plan for future. Usually those end users access those information using like a dashboard or some GUI. Those make them very convenient to get the data from their backend database. However, it's not flexible because they always only get the limited amount of information. Like if they want to join several tables in their database and query some information from the multiple tables, they cannot do it because the GUI or dashboard cannot provide it. Okay, so think about another scenario. We let those people to directly query the database. Is that it solve the problem? The answer is no, because you need those end users be a master of structured query language. But we know most of end users, they are not CS background. They even know that never write a single row of code. So they cannot do it. So let's think about the scenario.
I have a question. So sorry to interrupt. So is there any, for example, security reasons that you don't want the end user to for example, access the database directly?
Yes, they have data privacy. They have some regulation there but it can be controlled by admin. Say you can only to see this data. But you see, like for some managers or CEOs, they have their permission for all the almost the company data, but they cannot to query, to do any type of the query by themselves. Right?
Okay, because they don't do programming by themselves.
Yes.
Okay, I see.
Yes.
Thanks.
Yes. Yes, but yes, security privacy is in another side for trust. Yes. Good question. Yeah, so let's think of a scenario. They have a system, and this system can directly understand the human language and execute it against the database and the query information you need, so that everyone can simply talk to their databases in natural language. So this is the goal of today's topic, NLP meets database. We want to build a system for end user and the databases which consists of the two components. First component is from end user to the system. We call it human to database. That can understand the natural language queries and the data schema, the database schema, and combine these two to execute and query the structured information from a database for the user. And another direction is database to human. So this one is to study how to present this structured data to the end user. One way is you just present the raw data to the user, or you can choose to summarize the data, or you can draw the figured charts based on this structured output for the user so they can better to use it in their work. So first, we are talking about is text-to-SQL. So what is SQL? SQL stands for Structured Query Language. It is, I think, it is the official language to talk to most of databases. And why we care SQL? Because if you want to query your database, you want to query some important information like financial information, medical information, you need to know SQL. But a lot of people don't know SQL. How can we solve it? Okay, which means they need text-to-SQL. What is text-to-SQL? Text-to-SQL, they have three elements. First is the user who ask the questions for their purpose on database. Second is database, which store the database schema for those tables and the values. And third one is agent, which generate the SQL for these queries. The agent could be human or could be AI. And then the system will to execute this generated SQL and output the structured results to the user. Text-to-SQL, the input use the user natural language query and the database schema. And output is the executable SQL query. They have a big opportunity for text-to-SQL research because now more and more people from different backgrounds, they realize the big value in their data. They know if they can better to use their data, they can make a bigger whatever the business value or science value. So they are very urgent to find the flexible, convenient way to use their own data. And the text-to-SQL could make them life easier. So first, for the text-to-SQL, we are talking about the current research data sets on text-to-SQL. Because we believe the data is the field of AI, field of the machine learning system. And to understand the research data set, it also can help to understand the trend of this research area. First, I will say text-to-SQL dataset are scarce. Comparing to other large datasets, such as ImageNet, collecting text-to-SQL dataset is more time-consuming. First, it's very hard to find the high-quality databases from the internet, which have multiple tables. And second, when you have the table, you need to hire the people to ask the proper question about those domains, because those databases from different domains. And the third is you need to have the SQL master who can write the correct executable SQL for this database and the question. That requires very specific knowledge in databases. So that's why it's very hard. Because it's hard, at the early stage, the researchers, our pioneer researchers, they not collecting a very big text-to-SQL data set. They only collect the data set for one domain, which means in the whole data set, it only have a single database. The training and the testing are both using the same database. Because it's only one database and the number of SQL queries is also very small, or usually it's just hundreds. But you have data. So you can, with our pioneer researchers, they start to the text-to-SQL research. Those data sets, the good thing is it provides the data and cover the complex SQL structures and components. The negative is the size of the labeled query is very small, usually less than 500. So which means you cannot use it to train a large model. And second, when they collecting those data, for each query, they will paraphrase their natural question paraphrase the one natural question into 4 to 10 different natural questions. So when they do split, they just random to split those queries so that in the training and the testing, they may exist exact same query, but different natural language. So that when they build the model working on this data set, it's not a text-to-SQL data set. The text-to-SQL task is more like a text matching task, because just need to match this text with in the text to match the text in the training, you can get the SQL correctly. And second, because all those data sets, they only have single database, so that when the model you trained or designed for this data set cannot be generalized for the unseen database, which is not useful for now, because as I mentioned, there have billions of tables and databases there. And if you need to collect the data set and design a model for each database, it's not scalable. So we need a model that can be generalized to the unseen data after you train it. So which means you need to have a new data set. So in 2017, our team published a new data set called WikiSQL. We crawled 10,000 of tables from Wikipedia. And then we use some the template questions, and we hired people from the Mechanical Turk and to rephrase those questions and SQL, rephrase those questions in SQL. And we built a large data set. And for this data set, they have almost 10,000 schemas, so 10,000 tables, which is extremely, is much larger than the traditional data set. And also the number of natural queries is also larger, much larger than traditional ones. And the WikiSQL is first realistic the data set that can to extend the current extend that the previous text-to-SQL task into this cross-domain situation, and make it the most popular one. So the advantage of WikiSQL is huge. The number of queries and the database is huge. And second, it's the first data set it's emphasized the cross-domain. Cross-domain means the databases in a test set do not appear in a training or depth set. So that you need to so it requires the model you designed need to be able to generalize to the new databases. And disadvantage here is because when we generate our the queries, especially for the natural languages, we use some template and then we ask the human to paraphrase, to rephrase those queries. So it's not very, very natural. I mean, it's almost natural, but it's still not that natural. And second is all the databases we collected, because it's from Wikipedia, and we crawl a table from each Wikipedia article. So for each database, they only have one table. So that in this data set, in the SQL, there's no joint pattern in the SQL queries. And third one is this SQL does not contain the complex the query pattern like group by or nested query. So in 2018, a team from Yale University they built a new data set called Spider, based on a WikiSQL data set. This data set, they remove most of the databases. They only have 200 databases. But the size, the number of query and the number of questions and the query is still large. And they add more is add more the complex patterns. First, it make each database have multiple tables with foreign keys, so they have the joint the patterns in the SQL query. And second, they add the SQL patterns that the WikiSQL doesn't have, like a nested query, group by, or having. And it also supports this cross-domain. They split the database 160 in training, 20 in depth, 20 in test. And comparing Spider with earlier data sets, compared with some traditional ones, the Spider have larger number of query questions, SQL queries, and databases. And compared with the WikiSQL, it cover more different the SQL patterns that the Wikipedia doesn't. So the Spider dataset, we think, we believe that they cover almost all important the SQL components. And each table has multiple tables and several foreign keys. So it's good because in a real use case, the one database will have multiple tables. And third one, Spider is the first database. They cover these three properties. One is large scale. Second, it's complex. You have all the complex patterns. And third one is support the cross-domain for generalization. After the Spider dataset, our team and the Yale University's team, we have a meeting. So we discuss, is that mean we we don't, all the data set is in, so we have enough data set for the text-to-SQL research. We have a discussion, we find out no. Because most of those, the WikiSQL or Spider, they only focus on mapping a singleton or standalone utterances to SQL queries. They're not considered as a context-dependent scenario, because in a real-world setting, the user is not, many situations, user not direct ask a very long sentence about all the final goal they want. They usually will ask a sequence of a related question and step by step, and finally to achieve a complex goal. So our both team to collaborate and start to think how to build this context-dependent text-to-SQL dataset. We call it a dataset Spark, a dataset for semantic parsing in context, which published in 2019. The way is the idea. So we take a complex SQL queries in Spider. So we choose those questions and the SQL queries, and then we hire people. We ask them, this is the data, this is the question, this is the SQL query. We need you to decompose this question into several, a sequence of simple questions and a step by step. And each question depends on the previous question and their SQL queries. So that we have this, we simulate this context scenario for text-to-SQL. Spark is the first data set that have these 4 properties. The first, it demonstrates the complex contextual dependencies. And second, it's a large, it's have multiple database, a large number of databases, and each database have multiple tables. And third one is they have the SQL annotation for each step. And third is it requires generalization to new domains, the cross domain. Cross domain is a key for all the text-to-SQL data set we collect. Then after we publish this Spark data set, we get many people's feedback, and people tell us it's not natural, because when the people interact with the system to ask questions step by step, you cannot make sure, you cannot assume each step you always get useful information, and each step always based on previous step. Because so when the people ask these multiple interrelated questions, sometimes sometimes that step is not, they don't need to generate a query. Maybe they just to confirm some information, or even they may say no about some output. So they may have some negative response about it. So the best context-dependent scenario should be like a dialogue. So you should involve the dialogue into this text-to-SQL data set. So we improve the Spark and propose this Costco, a conversational text-to-SQL challenge. So to do this data set collection, we use the wizard of Oz method to collecting data. Wizard of Oz actually is a very popular data collection method that allowed researchers or even product people in the industry, they use to test a concept. It's a process that allows a user to interact with the interface without knowing that the responses are being generated by a human rather than a computer. So we hired some people from Mechanical Turk, some workers on the Mechanical Turk, and then in another side we hire some students who are master of SQL and tell them to pretend as a robot. And then we give the workers a question, a table, and tell them you are talking with a robot. You need to decompose those questions and make the robot can understand, and step by step finally to get the final goal of this question. So our users to talk with our students, and we collecting the data based on interaction. And in this process, so this is an example. So we given them a complex questions, and then the user will from these questions, and I'll also give them the table, so they see the table. So they will to ask some question. And if our students see, okay, this question is a good question. This question, all the information is very clear.
Sorry.
Yeah.
We have some question from the audience.
Yes.
I have a question. So you mentioned that you have to decompose the complex question to some simple ones, right?
Yes. Yes.
So why do you need to do that?
Because this is to simulate that when the people to ask some question, they may not know what exactly want to ask, or they cannot to express that full sentence one time. So they may start some conversation to ask some simple question first.
So and then what's the role of this complex question plays in this system? So this question is just an input or something that?
The complex question is the final goal for the user. So can think about it. This is your final goal, but because your system is not smart, right?
Okay.
They cannot understand it. So that is the complex question.
Okay. So this decomposition is performed by the machine or by human?
By human.
Okay. So the researcher will first decompose the complex question by themselves and feed into
but
the
not by this
system?
human, not by this human, by some other humans.
Okay.
Yeah.
Okay.
Yeah. Thanks.
Okay, got it.
Okay. Should I continue? Okay.
Yeah, please. Yeah, please. Yeah.
Yep. So when our student feel this question provide enough information.
We have another question. Sorry,
Okay.
we have another question from Victor.
Yeah.
Victor,
I just have a quick follow-up question to that previous question. Is this system capable of handling the complex question?
Is this system for this complex question, the accuracy is very low. Yeah.
But is accuracy higher for each, like if it's broken down?
So the current best the model for the hard question, the performance, I think it's like 30% accuracy.
Okay.
Okay. So the student will based on this user's input, and if they consider, okay, this user input is clear and it's all the information is given and simple, so then they will to write down that SQL for this turn, and then run and execute it against the database and get results. And then the student will, based on results and the SQL query, to write down a natural language response to the user, and user will continue. And sometimes the student may not understand or they have some confusion for users input. They will to clarify or to query to ask some question, and the user will to respond it to confirm, or they will to rephrase. So they will have different different type of interaction between the user and the fake bots. Yeah. So using this way, we collecting this conversational text-to-SQL dataset, and based on this dataset, we define the 3 different tasks. So first task is dialogue management, which is to predict the user's dialogue act. And second one is the dialogue SQL state checking, like to generate the SQL query based on the this multiple-turn natural language interaction and data schema. So it looks like the dialog state tracking, but the SQL state tracking is more complicated than dialog state tracking. The third one is the data to text response generation. So given your SQL query and your result tables, then generate a natural language response from them. Yeah, and this is the data statistics of this Costco data. Comparing with other data, the Costco, because it's collected using this dialog way, so they have some property other data set don't have. One is they exist the unanswerable question, and second, they have the user intent. So now they have different user intent. And the third one, they include the system responses, the natural language response, because previous data set they only have the text, the SQL query response. So it's more natural for real use case. So this is the the current research data set on text-to-SQL. You can see the trend inside. So it's from like the single domain and the single domain text-to-SQL to the cross domain, because more and more people, they want to have a system that can generalize from generalize to the unseen data, because the previous model is not scalable for these large demands for data query. And another one is from the standalone utterance to SQL to the SQL in a conversational in a context dependent scenario, which more close to the natural use. Yeah. So next, I will talk about the methods for text-to-SQL. So since the 1990, the first the text-to-data set ATIS was out, then people start to design and different model or method for text-to-SQL task. It starts from the traditional grammar-based the parsing algorithm to some database area they use in the human in the loop to design their database. And after the deep learning be widely used in the NLP, people start to use to build a neural network model for the text-to-SQL. And today I'm only cover some the neural network based model. I will choose the three typical papers to discuss. Yes. So the first one is a Sequence-to-SQL, which is generating structured queries from natural language using reinforcement learning, because that IO is very popular in 2017. Sequence-to-SQL, this model, it takes the question and the columns of table as input, and it they are using the augmented point network to generate the corresponding the SQL query. Different from other teacher forcing algorithm, which will stop at this generated SQL query and do back propagation. In the Sequence-to-SQL, during training, the generated SQL query will also be executed against the database, and the results will to match with the ground truth results. And if it's matched, they will give this query a positive reward, otherwise will be the negative. The motivation, they add this reinforcement learning and objective in this model is because given a question and a schema, there could be multiple correct SQL queries for the question. so that you using the reinforcement learning is more natural to handle this multi-answer situation. And we tested in the WikiSQL dataset because there's no other dataset in 2017. The results showed using this, adding this reinforcement based rewards can lead some improvement increase on the performance. I would say this is an interesting tryout using the reinforcement for text-to-SQL task.
Oh, sorry. I have a question. Can you go back to the previous slides?
Yeah.
So I'm not familiar with this kind of process, but I just wonder, I wonder, like this, you have a predict results and the ground truth results. So what is this result? I think you will need to use this result to compute the accuracy, right?
Yes. So for example, you have a question, you have schema, you have ground truth SQL, right? So you can run this SQL in your
SQL.
Yes, SQL.
So, okay.
Yeah.
So it's not like because it's a little bit hard for me to understand what is the SQL. Like the SQL is usually a number or something, but actually how to compare to like two different SQLs.
Oh, right. So so if you consider a SQL is a sequence,
okay.
So it's like a text sequence. So they just use teacher forcing to for sequence. Yeah.
But how to compare like the ground truth and the predicted results?
Oh, because so when you have the SQL, you can run database. Okay. Then you get the results of the executed results, right? So that you can do exact match because that you can do exact match.
Okay, so just so the accuracy is just computed by matching two sequence.
Yes, so they have two objectives. One is to matching for each step for the sequence. Another one is the result after you executed this SQL in a database. So they have two objectives.
Okay.
Yeah.
Okay, got it. Thanks.
Okay, so next one I'll talk is about write to SQL, which is relation-aware schema encoding and linking for text-to-SQL parser, which is published in 2020. Between the 2017 and 2020, they also have a lot of good papers, and those papers is more focused on like adding some type constraint or some SQL grammar like to constrain the decoding process. And this paper, they more focus on in the encoding part, how to encode some some explicit information to improve the encoder for text-to-SQL. So the idea is when we write a SQL query, the first thing as a human, the first thing is to look for different relations or some clues in the schema and the questions, such as you were to analyze the schemas, those in the schema they have multiple tables, you were to analyze their foreign keys, and so that you know the relation between the different table, or you will analyze the entities or column name in the schema and the entities in the questions, and see they have some there exist some words they can be aligned or matched between the question and the schema or all the table values. So like the example in this slide, they have 3 tables in a schema, and they are collected based on the foreign keys, which is important when you need to join those tables. And second, you see the natural language question and the schema, they have some word match. For example, in the question for the cars can partially match the name of title name of the tables like car data, car name, and car makers. So those is some information is important. And also like the word cylinder can align with the column cylinders in the car's data. So those relations is very important when we generate the SQL queries. WikiSQL is a paper. It's an approach that at first extract those relations from the input question and the schema, and then they will explicitly embed those relations into a neural network model. First, they defined the two different types of relations. First type of relations is the relations in a database schema. So they define some edge types in between the column and table, also column and column, table and table. So they define these 4 different edges between column and table. So for example, like just like a column table. So if the column X is a primary key of table Y, so they said this column and this table, they have a primary key F, edge type. And the opposite is not opposite. So if the X just the column of Y, but not the primary key, so they just say they have this belongs to relation. Yeah. So they're not just define the foreign key relation in a database schema. They also explicitly put those primary key or it belong to those relation in a schema of the schema. Another type of relation is called schema linking, which is some relation between your question and your database schema. So first type is called name-based linking. So name-based linking is, so if they have some words in your questions that can be exact or partially match some column name or table name, then they consider they have a name-based link between the word or phrase in the question and with this column or table. A second one is value-based linking, which is when they have a phrase in the question that can match some value in one column. Then they said, then they consider they have a value-based link between this phrase with this column. So they define this multiple different types of relation, and they add them to explicitly embed them in their neural network model. They using the transformer as their architecture to build their model. The transformer is a stacked self-attention layer with some position encoder in the first layer. So in each self-attention layer, they have 2 important components. One is the component to calculate attention score, which in some sense is implicitly to model different type of dependencies between the different tokens or positions. And the second one component is calculated the contextual representation based on the normalized attention score for information aggregation for each layer. So you can see the equation 2 on the right side. So in order to embed the relations, they found in the input and the input question and the schema, it makes some changes on the equation 2, which is the top one is for attention and the below one is for information aggregation. First it learns the the representation for each relations. And then if the token I and the token J, they exist, they have some relation, then this representation will considered as a bias be added into the formulations that calculate the tension between I and J, and also when they calculate this context representation for information aggregation. So they use, I just simply to explain how they do this, but if you want to know more detail, you can read the paper. So because they use this explicit way to model those relations, not just like other people, you just assume that a neural network can learn any type of relation by themselves. Using this way, they found they get good results. The WikiSQL outperforms all other methods by like 8.7%. And if you combine this WikiSQL with BERT, which is all the methods they will do this way to get better results, even after combined with BERT, this WikiSQL still significantly better than other models. And not just this. Right now, WikiSQL is super popular in the text-to-SQL area. I just do a screenshot today from the leaderboard on Spider dataset. The top three all top three using the WikiSQL as their method component, and plus with different the pre-trained model component as backend, and get the top three results. Even our company also use them, get the rank too. Yeah. So you can see how the strong the performance on WikiSQL, but although WikiSQL plus like BERT to get a very strong performance, but you can see like WikiSQL is a complex transform model, plus the BERT or other pre-trained model, they also type very big the transformer model. So over a transform model, you combine these two big transformer model and get like 8% improvement. Is it really worth? Are they? And this is the best way. Is there architecture redundancy in this configuration? So we ask this question to ourselves, and then we did some research, and also have some researchers are doing the same thing at the same time. So next, I want to talk about a paper called Bridge. The motivation is, like I said, recently, although we get a better performance, but the text-to-SQL architecture also getting increasingly complicated. So which also triggers larger training cost and the slowdown for both training and inference. So we want to explore if it's necessary to have this to increase the complexity of the architecture. So, sorry. So we explore the approach that approach that can capture in this table text cross model dependency, that only use the pre-trained transformer language model without adding more like WikiSQL or other layers in the encoder to learn those complex relations. So to do this, they have two tricks in this paper, two small tricks. First is in the encoder. So for the bridge encoder, the architecture is BERT, no change, just use BERT. even the auto parameters in the of BERT. We only made a small change in the input side. So in the input side, we add some the tokens for value. What it mean the token in value? So for the input this sequence, so first it's the natural question. We have SEP token. Then it's the column token for the table, and for each column, we will to do stream matching or other type of semantic matching between the tokens in your question and the value of this column. If there exists some values can match the tokens in the question, we will add those value after this column and add this V token to represent this value of this column. Yeah, so just it. That is a trick. We change the input sequence for the BERT, and this in some sense they make the relation between your question and the column more strong. So you can consider we implicit to, or we use a loose way to include the value-based linking in just from the input part. Right. And second is the decoder part. So the decoder architecture is also very simple. So on top of BERT, we add BiSTM to do some fusion, and then we use a LSTM single layer LSTM based model based the point generator to generate this the SQL sequence step by step. Very simple decoder, much simpler than other methods decoder. And we have a small trick in the decoding. We call it schema consistency guided decoding. So in the SQL, the syntax is first you have select, then it's from, then it's other conditions or other tokens about conditions or nested conditions. Yeah. But actually, when we write the SQL, first you need to know what table you want to use, right? Very heuristic. Then it's you doing other things. So in here we add those heuristic in the decoding. So we rewrite the SQL query and put the from clause in the front. So it generates from clause first. So you know, okay, what table, what kind of join you will do first. Then you generate others like select and other conditions. What it depends on what table you need. So you need to make it consistent. You cannot to use new table which not be generated in the from clause. So we call it schema consistency. And the result showed this is the report in the June 1st, and just this simple idea, a simple way, not adding any complex architecture, we get relatively decent results compared with other models. And it seems still not better than this the WikiSQL v3 plus BERT large model, which in the testing get 65.6%. And last week, my team told me, oh, they have some small bugs in my code. I made them change. Now we get this number, the 65% in the test, and comparable to WikiSQL plus BERT large. So it's very exciting. It also means, yes, they have a big redundancy in the architecture design in the previous models. And we're also doing operation study and to analyze the different component contribution for this bridge model. And we found the biggest if we remove the bird, we only have the by LSTM with that the LSTM point generator decoder. Only get the 48% decrease, but it's not surprised because that is very traditional sequence-to-sequence model. Of course, the performance is not good, and it's only one layer, right? But comparing with the WikiSQL, which also remove bird, they only have 8% decrease. So, which means although WikiSQL also combined with the bird, actually they have large redundancy, and our model is better to on leveraging the complexity and the capability of the bird model. So it's very interesting, and we see the improvement using the pre-trained language model as a backend encoder. So next, we want to discuss. Then we also want to think if they have some pre-trained model specific for text-to-SQL task. So first, before we talk about the model. So first, why we do it is because recently those pre-trained language models such as the BERT, Roberta, T5, BART, they achieve a great success on many NLP tasks like the GRU dataset, different classification problem, question answering problem, summarization problem, not machine translation, a dialogue, and etc. Yep. However, those language models are pre-trained only on the text. Right? They use in the Wikipedia articles, the book corpus, common cloud data for GPT-3. However, in the text-to-SQL, this table semantic parsing problem, the models not only encode the text data, it needs to also encode the tables. So it needs to join the understanding the questions and the tables. Yes. So to do this, we proposed introduce a new method called the Grappa. It's an effective pre-trained approach that to learn a joint representation of textual and the tabular data. And to train a model for the text-to-SQL, because they including the text data, table data, SQL data. So first you need to have the pre-trained data. But we know we don't have a super large like hundreds, thousands, or even millions, this type of data. So so in this case, sorry, let me have some water. Yeah, so in this case, we use some synthetic way to generate the pre-trained data. So first, we collect a large number of high quality tables from the internet. We spend a lot of time to crawl them and to clean them, and then we use a subset of the existing text-to-SQL data, and to induce a grammar from this data. We call it synchronous contextual-free grammar. And we use this grammar.
I have a question.
Yeah.
Here, you are using the grammar as some prior knowledge when you pre-train the model. So can you talk more about how do you introduce this grammar based constraint when you train this model?
Oh, sure. So to get a grammar, so we have the question, we have the SQL, we have the table. So we will to do some matching of the tokens in the grammar and the content in the SQL and see if they have some matching. So then we will to abstract it as some special token. So like here we have example. So this question, this question SQL, they will be like show the column 0. So column locations will match it to the column 0 in the table. So column 0 that have, so they defined those ops. It's more than, less than, less equal into those phrase. So they do some match. So they to abstract those questions and to into this abstract description, and then they do clustering, and then you can embed them and do clustering, and you choose the top 400. I think it's 400, almost like 400 to 500 clusters, and get them and to get them center to represent as a template. Okay. And then you can use this one with any table and to sample those columns into this template and to synthesize this data.
Okay, I see. Thanks.
Yeah, the more detail you can read our paper is in the archive. Yeah.
Okay.
Yeah. Yeah. So after you get this data, so you can start to pre-train your model. So we have two objectives in this pre-trained model. The first objective we call the column SQL semantic loss, and this loss is so the input is your it's the question and the column names and it's the data schema. So they include those column field names and table names. And for each column at their token at the tag token, they will to predict this column, what is the semantic low for this column when they do text-to-SQL. So given this ground truth SQL, so we can have the ground truth like a class, like for example, the class ID is not be used in this question. So the predict should be none. And for student ID, it be used for select, group by, and having. So they'll predict so it's a multi-label problem. So select, group by, and having. So use this way to build a relation, to make the model to understand what is the relation between your question and your database schema. Yeah. And the second loss is the MLM loss, which is a masking language modeling loss, which is used in all almost all those bird-like models. Yeah, and we add in the MLM is because it's trying to avoid to overfitting the synthetic data. Yeah, and we still use the WikiSQL as the method, and then we comparing with different the language model, because we combine with the WikiSQL and see the comparing results, and our performance is they have a clear improvement using this Grappa model as backend as a pre-trained model. And then after we get these results, then our people sit together and we found, okay, we use the synthetic data to do this pre-training, and this pre-trained model can improve the different text-to-SQL tasks. Then why not just to merge your synthetic data with a different text-to-SQL data set then just merge them and train them together. Can we also get the improvements? Interestingly, when we want to work on to start to experiment, they already have some researchers did it for us. So it's also the recent paper. They combine they comparing with synthetic data in the training and without synthetic data in the training. Okay, and they test in a different the text-to-SQL data set, and they found almost no change, sometimes even a little bit worse. And they are not just tested in the text-to-SQL data set, it's also tested in some the dialog state tracking data set. And they have the same conclusion. It's very interesting. We guess it's because when you combine, when you merge them together, your training may tend to overfit your synthetic data because it's larger. So that is our guess. So if someone can have have a paper can better to explain this, I think it will be very interesting, because in the text classification, especially for few shot, the data augmentation is a lot of papers show the data augmentation improves the text classification problem, text classification tasks. But in ours, we found it's different. So I think it's interesting.
So can I ask a question? So yeah. In your previous slide, can you go to the table? So this is a very general question because you've shown the result on the spider data set, right? And then some other data set
yes.
in multiple places. So you have the performance metric, which is a number, I think it's between 0 and 100. So I wonder, is this number the mean of the average result, or is it the best performance you obtained in your experiments? For example, your method get 69 points.
Standard mean.
Yeah, this is a mean.
Okay. Yeah. I think this is not the this is not maximum. It should be we run several times. But I'm not remember this is mean or it's max, but the difference is not big. It's a very small difference, I remember.
Right. So that's yeah. That's why I'm curious. Have you done some kind of a test, for example, paired t-test, especially for those methods? For example, the run SQL and with boot, right? That method is also very performs also very well, right? It's a performance metric is also like a 70.6, which is not as good as your best performance, but it's still close to certain version of your method with, for example, boot large or row boot large. So I wonder, have you done any like statistical test to see whether the difference is significant, the improvement of your method is significant or not?
Oh yeah, we didn't do that much of experiment because running them is not fast. But you're right. We should do more list. I think we were to think to add more results, but it also need to like ask other. Yes, I think we should do it, and other people also should do it. Yeah.
I see. Thanks.
Yeah. Okay.
So I have a question here.
Yeah.
So it's a very wonderful approach that your method can achieve such high performance in the spider dataset. So we know the spider is a very difficult dataset with complex and cross-domain examples. So have you do some analysis about your learner representations of your models, whether they have some transferable abilities which can improve the performance of your method?
We do some operation studies and analysis in the paper, but we don't have very the the clear conclusion on the why it's better, but we think it's because the Grappa model, when we train this Grappa model, we have that the semantic loss for each column. So it make it better to understand the relation between the column and the column in the database schema and the questions. And the bird model is more, it's because it only use the natural language to, and only have the mask language model. So it's more focus on the natural language understanding. So I think that is the advantage and the reason they get a better performance. But we don't have very good explanation like this transferability. Yeah.
Okay, thank you.
But it's important actually for the pre-trained language model. People use it for transfer learning, but it's still like I think this is it's very important research topic to understand what those pre-trained model can transfer, and what they transfer is important, because they also they have many people also have concerns, because you use a large unsupervised data to pre-train a model, and you don't know the quality of your data. So maybe there exists some like a bias, like ethical bias, or they have some toxic information, which may make a big the loss for if people when we really use it in some sensitive areas. Yeah.
Okay, thank you.
Yep. Thanks. Okay, so I think we have finished the main part of today's talk. Next, I will introduce some of our ongoing projects. So it's not finished, but I will still want to talk about it because they are interesting. Yep. So first, give an example. So give a table, a database. So this database you can have it's about the different cars. So just assume, imagine now you are driving on a highway, right? So but you want to query some information. So you ask your virtual agent, like a Siri or others, and assume like we have perfect text-to-SQL engine that can understand your question, which cars get more than 100 miles per gallon. I don't know why they ask this. Maybe they want to change their car. So in this situation, the text-to-SQL system can generate the SQL query and execute against the database and get an output. Like here, they have 4 records with several columns. And then you need to open your iPhone and watch it. You can't because you are driving. So in this situation, you hope your system can describe the output of the table for you. So like the system can do the text to the record to text generation and to generate the generate description for each record one by one. But of course, it's not the idea. Idea is you hope it can summarize the structure output for you, right? So we call it table summarization. So and the table summarization. Table summarization actually is very useful, especially for people want to get some information at any place. But when we started this project, we also still use Mechanical Turk to collecting data. We upload the tables and ask people to write their summaries about the table. Not surprisingly, the output of the summaries from the workers are different. very different. So then we divide this annotation task into two tasks. So first one is we ask the workers to highlight some cells in the table across multiple records that they think it can be summarized into one sentence. And then we send these highlighted cells to other workers, and they will then ask them to write one sentence for the as a summary. So we use this way to collect the bunch of table summarization data. Now we are still in the data collection and start some modeling work. Hopefully we will to release the data into public soon. Yeah. So this is one ongoing project. A second ongoing project is called Aqua. So what is Aqua? Aqua is the goal of Aqua project is automatically to generate visualization of structured data based on natural language description. Why we do it? Because many researches, the research, I think it's psychological research. They conclude the human is more sensitive to the visual information than text or some raw table data. Those visual good visualization can be much helpful for end users to get the insights from the data. So we collect a data set called Aqua, which we want to translate, and we choose a high-level visualization language is a WikiLite. So the goal is to translate the channel model using Aqua to translate a natural language question into this WikiLite language using the neural semantic parsing modeling. And then the whole task, they consist of the three components, three subtasks. First task, you need to get the field selection. And second one is field transformation. So this tool is very similar to the Text-to-SQL, but here is WikiLite. And third one is the very important one. It's the visual encoding. So how to visualize them, this visualization is a proper visualization, not like a random visualization. So this is what it's very cool, and our researchers are very excited about this project. And yeah, so hopefully this paper and this data set will release soon. Yeah. Okay. Yeah. So finally, so we'll do a conclusion for today's talk. First, I want to emphasize they have a large number of structured data stored in a database, and those data have the huge potential values until you can easily, flexibly to interact with them. And if you can do that, it can significantly improve everyone's efficiency in different areas and democratize the data query or data information for everyone. Here we try to build this bridge between the end user and the database, and hope and encourage more people can join us and build this together. Yep, so this is today's talk. Thank you for your attending. Thanks.
Thank you, Caiming. Thank you for the great talk. Yeah. So yeah, since we are only a little bit late, maybe for the interest time, let's take 3 questions before we finish today's seminar. So any questions from audience? Please raise your hand, and I will unmute you, and you can ask. Yeah. So maybe I have a question. So it's a follow-up question to my last question. So I asked you about how many runs have you done in your experiments to generate those results, right? And you mentioned that it took quite a long time to, even for a single run, it took quite a long time. So can you give us some like general, for example, picture about how many hours or how many days it takes for those for your team to train the, for example, to build a model, to train a model?
Usually it spends like days if you only have a single GPU, but if you have 8 like V100 GPU, it may take one day. Yeah.
So even 100 GPU, it will take a day,
Yeah.
1 day.
Yes.
Oh, I see. So
Yeah.
what's the bottleneck of this computation? What's the computational bottleneck for training, for example, BERT or other neural language models?
Because it's a complicated architecture. Even just the base BERT, they have 300 million parameters. So that's why it's slow. Yeah.
I see. So in your research, have you thought about how to accelerate the training of BERT or other?
Yes, we did, and so of course, if you have BERT, you want to accelerate, you can do if you for inference, you can have many ways, right? For training, we found some way like how to change the how to define different training strategy, use different optimization method, or change your objective. Like recently, the contrast learning seems it can in some situations we found in the BERT to train a BERT base, the contrast learning can make the training more efficient. Actually, this is some work I collaborate with some UCLA student, but I'm not sure I can. He wants me to say his name, but yeah. Yes, we are working on. We did some research on these areas. Yeah.
I see. Cool. Yeah, looking forward to the new paper you are writing with our student. Okay, so we have a question from the audience. Yeah.
Yeah, I have a question about the data visualization. So I wonder how can the computer know how to choose the histogram or the line chart when the customer asks the questions?
Yeah. So you need to have data, right? So we collect in the data. We generate a different. So given one query, we generate like 100 different visualization way, and then we use some the basic rule to remove most of them, and then we will have like remaining like tens the visualization output. Then we ask the people to watch it and to rank it. Yeah.
Okay.
So that's why this data set is very time consuming. We spend a lot of time working on it. Yeah.
Okay.
I see. So any other questions from the audience? Okay. So, we have another question.
Hi, thanks for the great talk. So I have a question about the usage of the semantic loss you mentioned. So I wonder. So you mentioned that this is sort of some sort of classification loss, right? I wonder if any specific choices of this loss, like should it be hinge loss or like logistic loss?
Here with the here we did it's like we consider each label independently, so it's like a cross entropy loss for each type.
I see.
Yeah. So we will enumerate all. I think like have 40 or 50 tens of different the rows. So for each row is a binary classification.
I see. Yeah, I'm kind of wondering, is the model kind of sensitive to the choice of the classification loss, or do you think you can pretty much use any? Like
we haven't tried different many different configurations, but I guess they will have some difference, but I don't think they will have big difference here. Yeah.
I see. Thank you very much.
All right. Okay. So for the interest of time, let's maybe stop here and we can take more questions offline.